So delta complex is nothing but an analog of CW complex. So in CW complex you consider n disks. In delta complex you consider n triangles. So first you start with unit vectors. You have at the ith position you have 1 lies in Rn plus 1. For example, for n equals to 2 you have 3 unit vectors E0, E1 and E2. And ordered simplex, this is a standard simplex, this is nothing but a convex hull of this set of the unit vectors. So for example, the 0 simplex is just a point, 1 simplex is just a line, connecting the 2 points, which will be 1 0 and 0 1. For a 2 simplex you have a triangle. So but this triangle, the vertices of this triangle are unit vectors. So this is a standard simplex. Vertices are E0, E1 and E2. So E0, E1 and E2. Now if you want to see it on the coordinate axis, you can say this is E0, this is E1 and this is E2. So this is how it will look like. And so this is the triangle. Then obviously 4 simplex would be a tetrahedron and so on. So more formally you write the simplex like this, such that all these TIs add up to 1 and each TI is positive. So that means all the points which lie inside here. So the simplex is this, all the points. So this is kind of a solid triangle. So all the points inside, they are these T0, T1, T2 in this case, whose sum is 1 and each of them is positive. Now obviously from this simplex you can go to a general simplex by a natural map. So you can see more details about this in the Hatcher. Now each of this simplex is ordered in the sense that you put it vertices in order, you label them. So you put the vertices like V0, V1, V2, V3, so on. So for a general simplex, instead of unit vectors, you could have any vertices. So you have a standard map from this standard simplex to any simplex. So for that simplex, you will have vertices like this, V0, V1, V2, all the way to Vn. So you put them always in order, small to large. So if vertex V0 is not there, you will write it as V1, V2, all the way to Vn. Or if you just have 2 vertices, say V0 and V3, you always order them from small to large. So you have ordered n simplex. So n simplex will have n plus 1 faces. So this is obvious. So this is 1 simplex, it has 2 faces, this and this. This is a 2 simplex, it has 3 faces, the edges. So this is one edge, this is another edge, this is the third edge. Now union of all the faces is called the boundary of the simplex and is denoted as this boundary. So this in rust color is the boundary of the simplex. So now we have talked about the simplices. Now we want to put a delta complex structure on any space X. So naively you can say delta complex structure on any space X is just decomposition into simplices, and that is the idea you need to keep in mind, that you're just decomposing a space X into simplices. But these simplices might not look like nice triangles. Instead of having a triangle like this, a perfect triangle, you could have something like this. So therefore you want to talk about something like this, there might be some deformation. Thus you talk about continuous maps from the simplices to the space X. So obviously first you talk about the interior of the simplex. So this is the interior of the simplex. So that is simplex minus its boundary. So on the interior the map is injective. So you talked about the interior, now you're talking about the entire simplex. So we have to consider the boundary. So on the boundary it will act on the faces. So act on individual faces. So there are 3 faces here. So the 3 faces here are the 3 edges. And this sigma I will act on all the edges. And then you have the special condition for every open set in X, if and only if the sigma IU is open in this delta complex. So this is to rule out some pathologies. So again you can find the details in chapter 2 of Hatcher. So now let us do some examples to see the delta complex structure. So we are now putting the delta complex structure on three things: torus, Klein bottle, and RP2. So for torus, you see this A and A are like this. For Klein, A is here and second A is in the opposite direction. Here A is going up, the second A is going down. So here again both the B's two edges are pointing in the same direction. Here again in the Klein they are in the same direction. Here in RP2 they are in the opposite direction. And HC is the same in all the three cases. So now we want to consider these maps sigma i's. So sigma i's acts face by face, as you see, face by face. So now we talk about the sigmas. So first you talk about the zero simplex, which is the vertex. So sigma is precisely acting on each of the faces. So total number of sigmas would be total number of simplices on the structure. So how many zero simplices? There's just a single vertex B in all the cases here. Again here there is a single vertex B. So zero simplex is just one vertex. Here there are two vertices B and W. Now you talk about one simplices. These are the edges. So there are three edges here, A, B, C. Again three edges A, B, C. Notice A is identified with A, B is identified with B. So there are three edges in each of the cases. Three edges here, three edges here, three edges here. All three have A, B, C. How many two simplices are there? So each of them has an upper and a lower triangle. You have this here, a lower triangle, and you have an upper triangle. So U and L. So you have two here, two here, two here. So total number of maps here is 6. Total number of sigmas are 6. And total number here is 7. So these are the total number of sigma i's. So because they act inside these two simplices also, and then on the one simplices and on the zero simplices. So now we have had three structures on which we were able to put a delta complex structure on.